Now that we've explored in the last two videos the basicity of amines, let's think about what these amines, these common medications that amines are in, look like when you put them into your body fluid, when you inject them into someone or when someone swallows them. What do the molecules look like, and how does that influence where they go in your body? So you zoom in on here. The first one we have here is Zoloft, antidepressant. And the amines are more basic than your body fluids. So the lone pair that you want to be able to see on these amines will steal a hydrogen from the water in your body fluids. So you'll do a proton transfer. The nitrogen will steal the hydrogen hydrogen separates from the rest of the water molecule. Now you don't have to draw the mechanism here, I'm just drawing it in. I'm going to erase the rest of that. That OH would go away, and this ends up forming a bond to that hydrogen. Now, whenever nitrogen has 4 bonds, it has a full positive charge, and so we create that here. And so when Zoloft enters your body tissues, it doesn't look the way that it was originally drawn. It doesn't look like this. Instead, it steals an H+ from your body tissues, or your body fluids, and it turns into what we have here, an ion, a fully positive ion. And we'll talk about the significance of that in just a second. For now, let's think about that same reaction with a couple more medications. Here we have amantadine. This is used to treat Parkinson's disease. So we have an amine on it. Whenever you see an amine, you want to see a lone pair that can act as a base. And because the amines are more basic than your body fluids, that lone pair will steal a hydrogen from your body fluids and become protonated. So the rest of this will go away as an OH-, and you'll form a bond between this nitrogen and a hydrogen. Now here, because the other hydrogens aren't drawn out, it may not be as clear, but does it make sense? This nitrogen would be bonded to 2 hydrogens, so that's 2 bonds. Then 3 and 4, the nitrogen has 4 bonds. Anytime the nitrogen has 4 bonds, it has a full positive charge. And so amantadine, when it's in your body fluids, does not look the way, that it was drawn at first, like this. Instead, it has this extra hydrogen and a full positive charge on it, and we'll see the significance of that in just a second. Okay, let's do one last one. We have phenylpropanolamine. It's used to decongest the mucus in your nose, so nasal decongestant. And whenever you see an amine, you want to see a lone pair on that nitrogen. And in your body fluids, that lone pair is going to be more basic than the fluid surrounding it. So it will steal an H+ from the water in that fluid. The rest of the molecule will go away as an OH-, and you'll have a new bond. Actually, let me draw this over here just because there's more room. You'll have a new bond to this hydrogen. And what you'll notice is that this nitrogen had 2 bonds already. Now we made a third and then a fourth. That's 4 bonds. Nitrogen, whenever it has 4 bonds, has a full positive charge. It accepted an H+, so it should make sense that we draw a new H and we draw a plus sign on it. And so when you put phenylpropanolamine in your body, it really looks like this. The nitrogen actually has a full positive charge on it and an extra hydrogen. Now what's the significance of that? Aside from the fact that the molecule changes a little bit in terms of its shape, ever so slightly, with that extra hydrogen on there, the positive charge helps to determine where these medications will go. The positive, one especially vivid representation of that is in your brain. When you're trying to get molecules into your brain, the molecules have to cross something called the blood-brain barrier. So you have these capillaries, so arteries, as they go from your aorta, which is big, you could fit your fingers in it. And when you go from your aorta to your tissues, your arteries get smaller and smaller and smaller until they're so small you can't see them with the naked eye. And those are capillaries. And that's the easiest for the blood to diffuse through because you don't have these thick walls of cells that are trying to keep the blood in. So nutrients in your blood are able to travel through the capillaries easily to get to your tissues. But You don't want just anything that you dump into your blood to get into your brain. Your brain is an extremely sensitive instrument, and if you often eat some crazy things, so you don't want everything you eat to get into your cerebrospinal fluid, the fluid that washes and supports your brain. So when the arteries course through your neurons, weave their way in between a cosmic web of neurons to feed them, other certain unique cells called astrocytes wrap around the capillaries to limit what can pass through them. You want nutrients to pass through, but you don't want other more complicated molecules to pass through. So here what we have is, in blue, we have a capillary in your brain. This long blue stick is a capillary traveling through a brain. And in green, we have neural cells called astrocytes. And what the astrocytes are doing are they're wrapping sort of tendrils around the capillary. Let's cut this in half and see what something like this would look like seen head on. You'd have your capillary, and then around it, the tendrils of these astrocytes will start connecting and making little connections on the outside of your neuron. And what you'd want to know, and so these would like branch off into other things, but what you'd want to know is that these astrocyte layers that are wrapping onto the capillary are really fatty. They're very non-polar. Fats are biological molecules that don't dissolve in water. They're non-polar. And so that layer of that astrocyte layer that wraps around the capillaries in your brain creates a barrier. It's called the blood-brain barrier. And when you're trying to treat neurological diseases or brain diseases, this is one of the most important considerations that you can have, is the blood-brain barrier. The blood-brain barrier prevents polar molecules from getting from your blood to your cerebrospinal fluid. Remember that like dissolves like. What that means is that polar solutes mix with polar solvents, and nonpolar solutes mix with nonpolar solvents. And so, because we have this nonpolar layer here around the capillaries, nonpolar molecules will be able to get through, will be able to get into your brain, but polar molecules, things that have charges on them, won't. They'll be stuck inside of your arteries. Okay, so if we go back to these amines, look at what we did. When we put them in body fluids, the nitrogen gains a full positive charge. That makes it very polar. Remember that polar is coming from differences in electronegativity. An oxygen, which is more electronegative than a hydrogen, becomes slightly negative. The hydrogen becomes slightly positive. This bond then has two ends, a negative end and a positive end. Another way of saying two ends is di and pole. Pole means end. For example, the two ends of the Earth are the North and South Pole. And so a dipole is a bond that has these two ends, positive and negative ends. That's a noun. If you wanted to describe something and say it's like a dipole, if you wanted to use an adjective version, it would be polar. And so as you can see in this example, water is very polar. It has these partial charges. Anything that has charges will mix with it because the charges on that polar thing, the positive charges here, would be attracted to the negative charges in the polar water. Nonpolar molecules don't have these partial charges on them. So for example, things like long hydrocarbon chains are nonpolar. They don't have any partial charges on them. And so it's hard for these to mix with polar molecules because these want to stick together and there's no way that this can butt its way in between them. It doesn't have any charges to attract one away from the other. So they don't mix. So by wrapping a whole bunch of nonpolar tendrils around your capillaries, there is a barrier that's created and nonpolar molecules get into your brain very easily, and polar molecules have a hard time. And because these amines ionize in your body and have a full positive charge, it makes it harder for them to get into your cerebrospinal fluid. And sometimes that's a good thing. You don't want them to rip it apart, but sometimes it's not a good thing because the amines are in a medication, and the medication is trying to treat a disease in somebody's brain. So there are other tricks that people can do. They can replace the hydrogen. They can sort of we know that you can make amines out of other molecules. You can make a precursor to amines that an enzyme in your brain will turn into an amine, and that's sort of how people get around it. They're called prodrugs. So if you there's a lot of interesting stuff to read about on that. I'll give you that key word. But a lot of prodrugs are drugs that are nonpolar enough to get through the blood-brain barrier, but that will be changed by the enzymes in your brain once they get through there to produce things like these amines. But what I want you to get from this video is that whenever you see a medication for the rest of your life, whether you're studying biochemistry in your undergraduate or pharmacology, or whether a drug rep is coming to you, whenever you see an amine, think of it as having an extra hydrogen and an extra positive charge once it's in your body fluids.